So 2.6 is all about function transformations, and as I sort of said at the beginning of class, this is sort of a pervasive math topic. Although function transformations 2.6, it's in our unit 2. We're going to see it again in unit 3. We're going to see it again in unit 4. We're going to see it again in unit 5. So it's like factoring. It's just one of the core skills, core ideas of mathematics that we really need to have down cold. So the pre-lesson activity I had you guys do was to see these function transformations in action, just to get a hands-on play with it using Desmos. I'm going to summarize it for you guys if you didn't finish, or maybe you're watching this video, in the future and you forgot what the pre-lesson activity was. So here I had you guys graph an absolute value function and change parts of the equation. Now, I'm showing all of the different parts at the same time. In the pre-lesson activity, I had you guys do it one at a time. It's the same concept. The first thing I had you guys do was add a random number to the absolute value function. So in this case, that random number is represented by C. So notice C is currently at 0, so this is the default absolute value picture. But what if I make C positive? That is analogous to adding to a function. You should have seen that as you add a number to a function, it moves the graph up, and as you subtract a number, it moves the graph down. Very easy concept. Adding to a function moves the graph up, subtracting from a function moves the graph down. If we do the same thing inside of the function, directly to the x, let's add directly to the x. Curious. As I'm adding to the x, it moves the graph left. As I'm subtracting from the x, it moves the graph to the right. So adding and subtracting seems to have a translation effect, but when you do it directly to the x, it's sort of backwards to what you think. Adding to the x is left, subtracting to the right. What about multiplying the whole function? So in this case, you can see here that the letter a is multiplying the whole function. Well, if a is bigger, say 2, 3, 4, we can see that the graph sort of gets skinny, gets very narrow. Because what we're doing is we're multiplying all the y values by a number bigger than 1. And what happens is those y values literally get pulled up or scaled up. The exact opposite, what if we multiply by a relatively small number but kept it positive? Say multiply by 0.9, 0.8, 0.7, so on and so forth. We can see it gets very flat. It sort of shrinks down. It's as if the absolute value was Play-Doh and then you just smushed your hand down on it. You just sort of flatten things out. So that's one observation we should have seen. And the last observation is, well, what if we multiply by a negative number? It flips the graph completely upside down. The last transformations I wanted you guys to see was, what if we did the multiplication directly inside of the x? I had you guys look at a different function because it sort of displays the characteristic nicely. I had you graph this weird, funky, spoiler alert, weird, funky sine function divided by the square root function. And notice I'm multiplying directly to the x. So I'm multiplying the letter d to both x's. Well, if I multiply by a relatively big number, multiply by 1, multiply by 2, you can see how it sort of bunches up. Notice the window isn't changing. It's still from 0 to 10, but I'm getting more squiggles in that picture. So it looks like the graph is like an accordion. You're squishing it all together. Interesting. When you multiply x by a big number, it gets squished in horizontally. What if I multiply by a small number, 0.9, 0.8, 0.7, so on and so forth? It gets stretched outwards. It flattens out. So just like with the translation, it seems to happen backwards when you multiply directly to the x. Multiply the x by a big number, it doesn't get bigger, it actually scrunches inwards. Multiply x by a small number, it doesn't get smaller, it actually stretches outwards. And not surprisingly, if you multiply by a negative number, it flips. But instead of up and down, left to right. Those pieces, those changes is what we call function transformations. And you perform those function transformations by changing parts or specific parts of an equation. Now, how are you supposed to know that? I hate to say it, it's just one of those math things that you just need to know. You just need to memorize. Just like how we memorize our times tables and our sums tables. But gee, I allow a note card on every single quiz and test. This might be a good thing to put on our note cards. Who knows? I'm not your parents. I'm not going to tell you what to do. Right. Even if I was your parents, I probably wouldn't tell you what to do because I wouldn't care. So let's go ahead and summarize. That's why I wouldn't make a great parent. Let's summarize all of our observations into a nice, neat chart here. So here are the function transformations. For any, and I do mean any, doesn't matter if it's absolute value, squiggle functions, square root functions, quadratic functions, doesn't matter. For any function, y equals f of x, and I'm going to, just like a pre-lesson activity, I'm just going to use the letter C for everything, and let's just suppose C is positive. Right? If you take that function and add to it, it will shift the graph up by exactly what you added to it. Add 2 goes up 2. Add 5 goes up 5. If you do the exact opposite and subtract, well, not surprisingly, it does the exact opposite. It shifts down. What if we added that C value directly to the X? Well, we saw it sort of went backwards. So it will shift left by C. And then what if we subtracted directly from the X? Well, it goes to the right. We also saw, well, what if we multiplied by the whole function by that C number? It will scale things vertically. Now, what we observed was, if I multiply by 2, it got stretched up by 2. Multiply by 5, it got stretched up by 5. Multiply by 1/2, it got flattened by 1/2. So it goes things, it's directly proportional. So, hey, we just did proportionality. So it scales by whatever you multiply by. Right? Sometimes math teachers, math professors, textbooks may use special words. I think your textbook does. If you're multiplying by a number bigger than 1, you're going to be pulling it upwards. Sometimes that's called a vertical stretch. So a vertical stretch is just a vertical scale by a number bigger than 1. If that C value, what you're multiplying by, is less than 1 but still positive, we sometimes call it a vertical shrink, right? Just know that the word stretches and shrinks are just description words of a vertical scale. The important thing is you understand that it's proportional, right? So I don't care if you say it's a vertical stretch by 2, it's a vertical scale by 2, I'll accept either. Just don't tell me it's a vertical shrink by 2, because that doesn't make any sense. Right? And we saw that the exact opposite happens horizontally if you multiply directly to the x. So that's going to be a horizontal scale. But we saw that if you multiply by 2, it got compressed inwards. It shrunk inwards. Multiply by 5, it shrunk inwards even more. So it's a inversely proportional relationship, so it's 1 over C. Right? If you multiply by 2, it's shrunken by 1/2. Multiply by 10, it's shrunken by 1/10. Right? But what are some fancy words that other people might use? So if you multiply the x by something bigger than 1, we sometimes call it a vertical compression, right? Because you're sort of, it's not vertical, sorry, horizontal. Anything happening to the x is a horizontal change. So it's as if you're playing an accordion, you're compressing it inwards. If that C value is less than 1 but still positive, we call it horizontal stretch. Last but not least are the multiplying by a negative. If you multiply the whole function by a negative, we saw that it got flipped upside down, but that's sort of like an Algebra 1 thing, that's an elementary school thing. The official math term is it's a reflection across the x-axis. So that's what flipping upside down is. It's a reflection across the x-axis. But we saw that if we multiply the x directly by a negative, you flipped it left to right. The official math description is a reflection across, you guys can probably guess, the y-axis. Right. Here it is, the granddaddy compiled list of every single function transformation you can ever do. If you want to change a function, these are the only rules, only things you can do to it. Right? And again, here's the easy and hard part. It's just something you have to know. You just, hey, Mr. Rowe, how'd you know it was up 2 left 5? You just do. You just have to know, right? So again, make it an objective to know this list, or hey, write it down in your note card. But we need to be able to know this. What are some expectations? What are some problems that you might be asked to do? I put them on the agenda there. One thing you'll be responsible for, can you read? Right? It's sort of weird. It's math class. But no, yes, I'm going to test your reading skills. So something that you may be asked would be something like this. Suppose the graph of f is given. Spoiler, it won't be. But pretend it is, right? Describe how the graphs of each function can be obtained from the graph of f. Right. So it'll be a multi-part example. Part A, part B, part so on and so forth. Right. So I believe I took that instruction straight from the assignment. So if you're doing the homework and go, what the heck does that mean? Well, just look back to your notes because I took the instructions straight from the homework. So it's going to give you expressions like, say, letter A, 3f of x minus 1. Right. And at first glance, this looks like a hard problem. How am I supposed to do this? I don't have the equation. It says they're going to give me a graph, but they didn't give me a graph. All this thing is testing you on is, can you read function transformations? I hope it's not, it's not hard work. Basically, the only requirement, do you have eyes? Well, I suppose if you wear contacts and you forgot to wear them or your glasses broke, you couldn't answer this question. But assuming your eyesight is good, I hope we can just clearly see there's an extra 3 here and there's an extra minus 1. I didn't do a lot of math. I just looked at it, right? And then you just got to figure out what's going on. That 3 is multiplying my function. That minus 1 is happening directly to the x. Being the good math student that I know this entire list, and I just so happen to know, there's no secret. You just answer it. You have a vertical scale by 3, and you have a right 1. That's the answer. If I solve 3f of x minus 1, I know there's going to be vertical scale by 3 and right 1. Boom, done, answer. Right. No calculations involved. You just have to be able to read it. Right. Doesn't matter how simple. Letter A was pretty simple. Or complicated it may look. Say, take a look at letter B. Negative 2f of 2 times the quantity x plus 3 minus 4. Holy Hannah, that's a lot of stuff. But all it is looking at what's happening to the regular function. Remember, the regular function is f of x. So I hope we can identify, and I'm actually going to make this negative its own shading. So there's a negative, there's a 2, there's this 2, there's this plus 3 here, minus 4. I'm not doing any math. I'm just doing a, do you have eyes? That you guys can clearly, obviously see those are the different parts that's happening. Then all you got to do, you have to know this list. There's really no way around it. You have to know these transformations. So, that's why the answer is going to be reflect over x-axis. This is a vertical scale by 2. This is a horizontal scale by 1/2. Remember, if you multiply by a big number, you actually compress things horizontally. This is going to be a left 3. This is a down 4. We answered the question. Question?
You know how you said that 2 becomes a 1/2?
Mm-hmm.
What if it was the other way around?
So let's say if this 2 was 1/2,
yeah,
then I would say it's a horizontal scale by 2. Right? Because anything that happens to the x is sort of like inversely. By 1/2. Right? So, again, hey, Mr. Vo, how'd you know it's left 3? Hey, Mr. Vo, how'd you know it's vertical scale by 2? There's nothing to calculate. You just have to know this function transformations. Right? So, you can see why I said that this is going to be a very easy section or a very hard section, depending on whether or not we know these. Okie dokie?
Yes.
Okay. What other things do I expect you guys to do? Well, I asked you guys to read function transformations off of a generic function. I didn't give you a real equation. I expect you to be able to do the same thing once I give you real functions. For example, explain how the graph of G is obtained from the graph of F. And we're assuming they're going to give us the graphs. And you know what they say about assumptions. They never work. That's exactly what they say. No, they're not going to give you the graphs. Instead, they're going to give you the equations. Say, for example, letter A. Let's start off easy, then we'll look at a very ugly function. Suppose f of x is 1/2 raised to the x power, and g of x is 1/2 raised to the x plus 7th power, right? Certainly, one thing we can do is just graph them and look at the changes, but, what if we don't have Desmos? What if we don't have a graphing calculator? The way you see function transformations from actual equations is when you guys were little, like, 5th grade, not 5th grade, 5 years old, 6-year-olds, 7-year-olds, did you guys ever read those picture books where, like, it's spot the difference games?
Yeah.
Where they give you two pictures are really almost similar, but little thing there's different. You have to find out what's different. That's basically how you tackle this problem. You have to look at this function. You have to look at this function and just play the what's different game visually. Don't tell me up, down, left, right. Just very superficial, scraping the surface, like very dumb, obviously dumb answer. What is different between this function and this function? The +7, right? I think this wasn't, where's Waldo? He wasn't hiding. Clearly, the +7 is the only thing that's different between the F and the G, right? Oh, forgot the equal sign, thank you. Okay. Now, this is where you got to do some mathy stuff. Not a trick question. Red flag, warnings. Not a trick question. I started off with nothing. Ended up with a +7. Mathematically, how do you go from nothing, 0, to a +7? You add 7. You plus 7. No duh. Now, this is the thought process you as a student have to ask yourself. Okay, I figured out it's +7. Is it +7 directly to the x or to the whole function? Directly to the x, and then you being a good math student, knowing this entire list, know that adding directly to the x is left. So left 7 is the transformations that are present. That's it. That's all you got to do. Can you spot the difference? Can you read? And can you interpret? Okay?
Yes.
Let's take a look at an ugly function. Letter B. Hey, let's do a function I've never taught you. Let's do trig. Doesn't really matter. F of x equals, I don't know, cosine of x plus 2 pi plus 3, and then g of x is 2 cosine of x plus 7 pi minus 1. So go back to the first grade, the second grade, the third grade, your picture book. Spot the difference. What's different between these two functions? One has a 2, the other one has a 1. The 7 pi and the other one has a 2 pi. One has a plus 3, the other has a minus 1, right? That's it. That's all the differences. Now remember, the question says you start at F and go to G, so don't read it backwards. You're starting at the top and going at the bottom. So let's start with the yellow. Okay. You start with 1. Remember, there's a 1 here, even though you can't see it. You start with 1, you end up 1 cosine, and you end up with 2 cosine. Mathematically, what did you do? Multiply by 2. Am I doing it to the whole function or directly to the x? Whole function. Multiplying by the whole function by 2, you should know is a vertical scale by 2. Move on to the blue. You start with positive 2 pi plus 2 pi. You ended up with plus 7 pi. Mathematically, what did you do? You added 5 pi. Did I add it directly to the whole function or directly to the x?
Yeah.
Directly to the x. Adding to the x is to the left. And then move on to this color. Positive 3 to negative 1. What did you do? You subtracted 4, which is subtracting 4 to the whole function, is down 4, yes. Trying to go through the whole logic, because this is notes after all. Yeah. That's it. That's all you have to write. Oh yeah, to get the G graph, you start with the F graph, scale it vertically by 2, shift it left 5, and down 4. Easy peasy? Left by 5 pi, yes, thank you. So being able to read or spot the differences and then read the transformations is nice, but we should be able to go backwards. If I give you the transformations, we should be able to produce the equations. For example, if f of x equals, let's just do the square root function. Right? I could have used the absolute value function. I could use the quadratic function. It doesn't matter. If f of x equals the square root of x, what would be the equation of the function? Let's do f of x. What would be the equation of the graph of, I dropped off 2 words there. What would be the equation of the graph of f of x vertically scaled by 2, reflected over x-axis, shifted down 5, and right 3. Oh boy. Lots of stuff in that question. The first thing I would do as a student, just pick out the information, pick out the transformations. And they're very obvious because, well, they tell you. So I got one transformation here, scaled vertically by 2. Another transformation here, reflected over the x-axis. Another transformation here, shifted down 5. Another transformation here, right 3. Then what you do is you just start with the template that they gave you. The template is square root of x. And then you just have to know your chart. All right, let's start with the yellow. How do I scale something by 2? Just multiply by 2. Multiply the x or the whole function? The whole function. So there is your scaling by 2. How do I reflect over the x-axis? Make it a negative, yeah. How do I shift it down by 5?
Minus 5.
To the whole function or directly to the x? The whole function. So there's your minus 5. And how do I go right 3? Minus 3 to the whole function, directly to the x. Directly to the x, minus 3. Guess what? You built your function. That is the, erase, or undo rather. That is the equation that you built. Easy peasy. So with function transformations, I expect you to know them. I expect you to read it, whether or not I give you an abstract function or an actual function. I expect you to build functions off of transformations. And last but not least, the sole reason why we study transformations, I expect you to graph them.
Yes, sir.
Question?
So if it said reflect over the y-axis, you get rid of the negative from the 2 and put it where the x is?
The question was, well, what if it said reflect over the y-axis? Would you get rid of the negative in front of the 2 and put it with the x? The answer is yes. But you have to remember that you have to multiply to the inputs. And now, do you agree that the original function was this? The input is inside the radical. Mm-hmm. So if I wanted to change this part into reflected of the y, it would look like that. I have to multiply the entire input by the negative. So that would be right 3 reflected over the y-axis. Good question. And last but not least, sketch. Right? What if I ask you to sketch f of x equals x minus 1 squared plus 2? Right? Normally, what would sketching entail? Well, normally what would sketching entail if we didn't have a calculator or Desmos? Because I know that was going to be the first response. You would just do XY table. That's it. Easy peasy. Just make an XY table, plug in some X's, get some Y, plot it, go home, be happy. But you know what? Sometimes the function gets crazy. Sometimes I have big numbers. Sometimes I just don't want to spend 3 minutes making an XY table. How can I sketch this really quickly in about 30 seconds? Just use function transformations. I hope we can just read. We have a -1 here and then a +2 here. Not too hard. So we have right 1, up 2. Hey, Mr. Bo, how'd you know it was right 1, up 2? Because I just know the list. There's no calculations involved. You just know it. Now, would you guys agree, if I were to take the highlight out of the equation, what would be left over is an x and a squared? If I took out all the bells and whistles, took out all the transformations. So we should know what x squared looks like. We learned that last year. X squared is a quadratic. The shape of a quadratic when we graph it, it's a parabola. So I know it looks at 0, 0. 1, if I squared them, would give me 1. 2, if I squared them, would give me 4. And then, of course, it's symmetrical on the other side. Right. So these, what are called parent functions, should be easy for us to sketch because we can just do a quick mental sketch, right? So that took me, if I weren't explaining, that would have taken me about 5 seconds. And then to get the actual picture, to actually answer the question, graphing f of x, what you do is just listen to the transformations, right? So I have a coordinate system. I'm going to make my tick marks. 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then all I'm going to do is do the transformations, right 1, up 2, with these points here. So I have the luxury of using a different color. If you guys want to use, light pencil, dark pencil, pen, whatever you guys want to do in your notes is your business. So let's move the origin here, right? So I'm just going to listen to the instructions, right 1, up 2. So for this point here, the origin, I'm going to go up right 1 and up 2. So 1, 2 should be my new location. Let's move this point 1, 1 here. Right 1, up 2. 2, 3 should be my new location. Let's move this point here. 2, 4. Right 1, up 2. So 3, 6 should be my new location. And of course, you can do it for the other points there. Guess what? What would have taken about 3 minutes to do an XY table, we sketched in about 30 seconds, just by using function transformations alone. Right. Function transformations, A-okay? Right. Several objectives for today. Number 1, I expect you by the end of today know what they are. Number 2, be able to read the function transformations either from a generic function or a specific function. Number 3, build equations. And number 4, sketch using function transformations. A little footnote, little caveat when you're sketching or applying function transformations. Function transformations follow order of operations. That's PEMDAS. Please, whatever you guys want to call it. Order of operation, PEMDAS, GEMDAS, grouping symbols, whatever. Now, when it comes to function transformations, we only have 2 operations, multiplication and adding, subtracting. Adding, subtracting is the same thing. Right? So the rule of thumb when it comes to function transformation, scaling always goes before translation. So if you have a vertical scale and then shift left, right, up, down, you always do the scaling part first before you do the shifts. Okay? Same thing with flips, reflections. Reflections are multiplying by a negative. So you do scalings and reflections first before you do shifts. Okie dokie? Well, that's it. That is 2-6. A simple concept, but it's hard in the sense that you got to memorize it, you got to know it. But if you know function transformation, every single function we'll see this year will be a piece of cake.